It's on. Good. Okay. Okay. Okay, so we might start. Thanks again for being interested in coming and for understanding these lectures. So there will be different things that we will try to cover. I decided somehow to start from very basic stuff. So the lectures today will not be really focusing on NV centers and those, but a kind of reminder of spin 1/2 physics and also on magnetic resonance. Tuesday, tomorrow, then we will start the lectures on color centers. And I will not start by describing this, but another defect in the solid state, which actually was thoroughly investigated in the past, which is the F center in alkalides. And basically, this is a very simple system to model, and we can learn a lot of things with that. And after, there will be a kind of straightforward connection to other kind of solid state defects, especially those of diamond. And I will review a little bit the basic properties of the NV centers and why it can be, it has been so successful for sensing applications, leading to myriads of applications and an amazingly number of team working on using this very specific defect. Also, and then we will maybe in those days, we will focus on how we can really probe magnetic field and going into the detail of that. There will be, I guess, a lab demo in Professor Kamal Pising lab. Then on Thursday, what I would plan to do, depending on how fast we have been, it's showing you how NV centers can be coupled to nuclear spins in the diamond. And this is very interesting for some also other kind of sensing application. And the lab demo that we will try to settle in video conference using video link will be more focusing on that. How you can play with nuclear spins using the detection of the NV centers. And on Friday, we'll discuss some emerging application, and I would especially like to discuss how we can use NV centers to probe superconductors at high pressure. And this is my current main research topic at the moment. Okay, so let's start these lectures by the wonders, I call that the wonders of spin 1/2. If you want, you can download the PDF version of that, and this is, I hope it's going to work. You tell me if this works or not. And normally, you can download the PDF file of the systems of what we are doing. It works? Good. Good, good. I try to do that. But okay, let's start by a quick reminder. Many of the applications on NV centers will be based on the Zeeman effect. The Zeeman effect is the influence of a static magnetic field on a neutral atom, and it was discovered at the early 20th centuries, in the very first years of the 20th centuries, by a Dutch professor, Peter Zeeman, in Amsterdam, who observed that the emission, that's for instance the emission of cadmium, and if you look to the spectroscopy of the emission of the line, it has a very bright line in the red. And if you now apply a magnetic field, you see that here each line is split into, in that case, 3 components. That was explained by the famous Hendrik Lorentz, and they both got the Nobel Prize in Physics for that citation, in recognition of the extraordinary survey they rendered by their researchers into the influence of magnetism upon radiation phenomena. Actually, people tried to observe this magnetic field could have some effect, and very famous people tried that. Faraday tried, but didn't succeed in observing anything because the effect is very tiny, and you required very powerful spectrographs to observe that. And that was really the achievement that Zeeman was able to do, to have a very good spectrograph and be able for the first time to measure the splitting. Actually, it was not really a splitting, it was just a broadening of the line, and Lorentz explained that. And the explanation was that, of course, this was far before the event of quantum mechanics, so we just considered the influence of the magnetic field on an electrically bounded electron in the system, the famous Lorentz model of the atom. So if we now take the force applied to the electron as this one, the elastic bounding term here, and the coupling between the speed of the electron with the magnetic field, and this is a uniform magnetic field pointing in the z direction. You have very simple equation of motion here, and those equation of motion then will you can easily solve them, and there is of course just an oscillating electron at the frequency omega equals square root of k, the constant that bounds the electron in the system, divided by the mass of the electron. And for x and y, you have coupled terms that are somehow circular orbits of the electrons, and with different frequencies, omega 1 and omega 2. So you have 3 frequencies of the system. Only one frequency, omega 0, if the magnetic field is equal to 0, and now 2 other frequency appears if you apply a magnetic field. And if we now suppose that the influence of magnetic field is weak, the 2 frequencies are separated by delta omega, and delta omega is the electric charge of the electrons times the magnetic field divided by 2m. Okay, and they will come back to that. We see already some important parameter which only depend on fundamental constant, the electric charge and the mass. And that's why somehow it was something very important, because it tells us something about the interior of the atom. And now we can look to the dipoles that are induced in the atom. So we have here at omega 0 just an electron oscillating along the z direction. But if you will look at the 2 frequency omega 1 and omega 2, which with this difference delta omega, they have circular orbits, and the circular orbit is orbiting in one direction at a given frequency and the opposite direction on the other side for the other frequency. And now we simply need to take into account the radiation from these 3 independent oscillating dipoles at those 3 frequencies. And for that, we come back now to, sorry, the title is in French, but to how an oscillating dipole will radiate. That's a standard formula from electromagnetism. We take the oscillating dipole, we have the potentials, and from the potentials, we can calculate the electric field that is produced by this oscillating dipole. And from that, if we are far from the wavelength lambda, a distance far from lambda, you have very simple expression. The electric field is transverse with this formula, and the dependence over 1 over r, and just a plane wave propagating in this direction. and the magnetic field is perpendicular, as we know. This is very simple results from basic electromagnetics. And this is the oscillating of the dipole, as we can see. But what is also important is the fact that the field from radiated by the dipole has a linear polarization, which is defined by the projection of the oscillating dipole onto the plane, the plane perpendicular to the propagation distance, as we know. So now, if I come back to that pictures, I just need now to see, to project the oscillating dipole onto a given plane, and that will give me specific polarization. And this is what we will show now. Once I'm here, I can now see what we have. I can look, for instance, in two different directions. I can have a look to what we see from here, Okay, I hope you see it here, from the longitudinal direction. And in that case, I will see it's here. This dipole will not be able to produce some radiating field. There will be only two circular polarization, sigma plus and sigma minus, and those are separated in frequency by delta omega, with delta omega, reminder, is the charge, the electric charge times the magnetic field over 2m. And now, if we look transversely, the field is detected on this transverse detection. We observe now linear polarization here, perpendicular linear polarization here, and linear polarization from this dipole. So we have now three lines, like what's in the picture I showed you, where one, the red emission of the cadmium atom was split into three components, and we have this, and you can have this, you can check that they are differently polarized, associated to this simple model. So what's remarkable is that there is a perfect agreement with the experiment. But how now can we model that, these results using quantum mechanics? And for that, basically, just a quick reminder about, and we will use that in the following, about the angular momentum in quantum mechanics. If we start with the orbital motion of a particle, the angular momentum is defined by the operator R, that defines the position of the atoms, times the P, the momentum, and we have these three components, Lx, Ly, Lz, and we can also use these three components to compute the L square, which is just Lx square plus Ly square plus Lz square. And in this representation of position, Lz is equivalent to h bar over E x dx d over dy minus y d over dx, acting on the wave function defined as a position of the position of the particle. And using that, it's a very simple exercise to show that Lx is not commuting with Ly, and there are these fundamental commutation relation linking the three components. This means that you do not have joint eigenstates if you take two components of the vector operator L, but since Lz, for instance, is also commuting with L square, then you can find a set, an ensemble, a set of eigenstates which are joint eigenstates for both Lz and L square. And this is what we usually do. And we will call Lz and L square Jm, okay? Using the Dirac's notation. Okay, now this can be generalized, and now we will define an angular momentum operator J as with three components that verify the canonical relation of commutation between Jx, Gy, etc., like what we demonstrated before. So we have the joint eigenstate Jm. At that point, I do not know what J and M can give. But nevertheless, there is a theorem that tells us that since J square will have an average value over any state psi which will be positive, then all eigenvalues of J square have to be positive. And we choose at that point to write them by convention, like this one, J square acting over Jm is equal to h bar square, J plus 1, Gm, and G has to be real positive, and the same for Gz. Okay, and again, this parameter has to be again real because it is an Hermitian operator. Okay, now we introduce the ladder operator, plus minus, which are combination of x and y operator of this angular momentum, and they are Hermitian conjugate of each other with this relation. And now it's not difficult to say that if we apply those operators on Jm, then the influence of this operator is to rise or to decrease the m value by plus minus 1. Okay, this is you find that in every quantum mechanics lectures. So the action of this ladder operator, plus or minus, will create a gap, delta n equal plus minus 1, and that's why we call them ladder operator. Okay, now I will use this ladder operator to demonstrate some properties of the two main parameters G and M. Okay, so using that, since this is a positive operator, it already puts a constraint between M. M is bounded between a minimum value here and a negative and a maximum positive value that we have here. So we have this constraint for M value, okay? So at the same time, this tells me that somehow, if I take this negative, the ladder operator that decreases the M value, they're acting on this minimum M value for the ket, for the state, then I will get 0. I cannot go below, okay? M minimum is the minimum value of M. At the same time, there is a maximum value. And if I define J plus on this value, then I will have 0, okay? Okay, so, and now to determine this minimum and maximum value of the M quantum number, I can proceed as follows. I start from that which is 0. On this side, then if I act J plus, this will also be 0, okay? Because, of course, any operator acting on 0, the number will give 0, and the same on the other side. And from that, you can easily realize that by some very simple form algebra, the minimum value of M, the quantum number M, is minus J. And the same for G, sorry. And the same on the other for the maximum value of the quantum number M. So somehow now I have a relation that bounds the M quantum number. And I can use that. It's just a brief reminder of what you have learned in quantum mechanics. We can apply now, step by step, the quantum number. So if I start from here, Jj, it's a maximum value I can have. I apply J minus, get J, I will then obtain J minus 1, and I continue like that down to J minus J here, the minimum value of the quantum number M. And if we reapply this parameter, this operator, then I got 0. I can again start from this, apply now J plus, and I will go to Jj as a maximum value. So I have this chain of value, and that has to be closed. So to close that, we just need to count the number of steps we have, and that's 2J. So this is a closed chain only if 2J is an integer. So they set the different value of any angular momentum in quantum mechanics, as you know. It can be null, can be 1/2, can be 1, can be 3/2, can be 2, etc., etc. So I have this integer and half integer values that are possible. The electron spin, proton spin, as we will see, will be spin 1/2. And the NV spin will be 1, as we will see later on. Okay, now and for that, I can compute, depending on the different values of J and M, the eigenvalue of J square, the operator J square, and the eigenvalue of operator Jz using this very simple formula. Okay? Now, what I can do more, again, it's some reminder of quantum mechanics, but we will have to use that after. That's what I want to take to remind you, this very simple quantum mechanics results. I can try to define now the eigenstates of angular momentum. This is, again, done using the ladder operator J plus minus acting on the state Jm. And then I have this simple formula that tells me that somehow I have this state, Jm, define an orthonormal basis of the Hilbert space associated to the angular momentum J. And the dimension will be 2J plus 1. Okay, now I come back to the orbital angular momentum and the eigenvalues of L square and Lz. We switch to spherical coordinates and we look for the wave function psi over r theta phi. And of course, what I need to take into account is how these operator L square and Lz act on this wave function defined into the spherical coordinates. Then it's simply L square. I know it's h bar L plus 1, the wave function. Lz acting on this wave function will be m, the quantum number m, times h bar times the wave function. Okay? And this can be, now I just need to remind you that the Lz operator in spherical coordinates is simply h bar over I times the partial derivative with the angle phi. Now, if I take that into account, I put this expression here, and what I obtain is that the dependence of the wave function as a function of this angle, this azimuthal angle, is simply the multiplication of psi times I times the quantum number m. So I have this very simple formula now that tells me that the wave function associated to the orbital angular momentum L is simply E exponential I m, the azimuthal angle, and a function that depends only of r, the distance to the origin, and the polar angle theta. So I have decoupled the angular dependence, radial and angular dependence. Of course, the condition for an orbital angular momentum is that if I turn by 2 pi, the wave function will come back to the same value. Okay, so psi take as function of r, polar angle theta, and azimuthal angle plus 2 pi should be the same as the one I started from. And that, of course, if I take this value, this has a constraint. M is then an integer. And since M and L differ only by an integer, then I know that the value of the orbital angular momentum L is only positive. So that tells me that somehow among the value positives, the value I obtain here, only those are possible for an orbital angular momentum. So up to now, I demonstrated that there are possibilities to get value of 1/2, 3/2, but these are not allowed due to the symmetry condition for an orbital angular momentum. Okay, now what I need to do is again, my purpose at that stage, it's really to have a quantum mechanical model of the Zeeman effect. So I know how to describe the electron circulating in the atom using the wave function I obtain. Now what I need to do is to see how the magnetic field will influence the quantum states. So for that, we need to get the Hamiltonian. And to get the Hamiltonian, this is not very difficult, but somehow it's a reminder. But somehow I would skip that. But the only purpose now is that we have in the Lorentz, using the Lorentz condition, taking into account the potential, vector potential A and Coulomb potential phi, we have this expression, okay, that you might know. And this is not so difficult to obtain. Basically, it's what you have, p squared over 2m, what you have usually but you need to modify the momentum by the potential vector. And this is just due to the fact that somehow you need to retrieve the Lorentz force. So somehow you start from the Lorentz force and you construct the Hamiltonian in a way that it will recover the Lorentz force, okay? And you identify like that the conjugate variables that you need to do. Okay, once I do that, then it's a little bit now of machinery. We suppose that we have a uniform magnetic field. So the potential vector is defined by -1/2 r times b, cross vector b. And then we have, and this, we can enter that into the expression of the Hamiltonian, taking into account the charge of the electron. And we do some simple development, and it's a little bit a few lines of calculation. You find that in whole textbooks of quantum mechanics. And basically, you separate the terms into two components. In one of the terms, it has a very simple expression. It's simply p squared minus e times 2. And this 2 will simplify with this one. And you see the product of the Lz, the operator, times the magnetic field. And there is a second term here, which is proportional to b squared. So we have two terms, one proportional to b and one proportional to b squared. And we can rewrite the linear term in this way. So the linear term will be a perturbation, which defined as mu b. There is a mistake. Dividing by h bar, Lz, the angular the orbital angular momentum operator times the magnetic field. And we have introduced an important parameter that we'll see quite often, which is the Bohr magneton. And the Bohr magneton is also defined only by fundamental constants, the electric charge of the electrons times h bar, the Planck constant, divided by 2m, the mass of the electron. Okay? So this is the magnetic dipole that I can associate to a single electron, and we will see how we can reobtain in a completely different way the Bohr magneton. Okay, now the second term. This term, which is proportional to b squared. Now if I can do some order of magnitude, you can easily realize that if I take, for instance, the levels of the hydrogen atoms. The hydrogen atoms are separated by energy difference of frequencies in the optical domain. And those now, if I take into account the order of magnitude of this term, it would lead to difference of energy, which is of the order of mu b times h, and that are typically depending of usual magnetic field that can be applied, and we will come back to that. They are smaller by the frequency differences associated to the Hamiltonian of the atom in vacuum. And if I now look to the second term, proportional to b squared, you can show that there is the same energy difference. So somehow, this compared to this one, it's the order of magnitude of this one compared to this one. So somehow, I can, if I remain to somehow the first order perturbation, I can only take into account this term and forget, and I can forget the terms which is proportional to b squared. And this is responsible for diamagnetism. the order, as you might know. Okay, now I'm just coming back to the influence of the magnetic field. So it just, I have different ways. Now I know how to explain how the magnetic field will impact the quantum states of the atom. The quantum states are associated to NLM. If I take, for instance, an atom like the hydrogen atom in vacuum, I apply now, and I see immediately that the perturbation corresponding to the magnetic field is diagonal in this basis of this eigenbasis of the atom. So if I write, for instance, what happens for an angular momentum L equal 1, I have these terms, and what I see is that each line now is split into 3 components. Each of those components are associated to a given value m, okay, m equal minus 1, m equals 0, and m equal plus 1. Okay, so I see now 3 lines depending 3 new eigenvalues, and somehow I can rewrite them as delta E, the difference of energy, as a function of m times j, I will come back to that, the geomagnetic ratio, times mu b times the magnetic field. And this j factor is also called the Landé factor, and is equal to 1 in my simple explanation here. Okay? So I have 3 lines, and they are exactly where I expect them from the classical calculation that Lorentz did somehow to explain the Zeeman effect. So, and you can also show that, for instance, the transition from the ground state L equal 1, n equal 1, L equal 0, to, for instance, this line will have a linear polarization as in the classical explanation, where this one and this one, well, I change the m value by plus 1, means that somehow I need a photon which can take this extra angular momentum to couple to the atom, and this explains the secular polarization that I explained for detection in the longitudinal direction. Okay, so everything works remarkably well. I have both the classical computation, I have both, and now I have the quantum computation experiment, the quantum mechanics calculation, and they do agree. So unfortunately, there is the anomalous Zeeman effect. And the anomalous Zeeman effect is the fact that, for instance, if I take now the D line, the 2 emission line of the sodium atom, what I see is that these lines, instead of producing the amount of components that were previously odd, I could obtain either, for instance, 3 components when I looked perpendicular in the perpendicular direction to the B field. Now I see a number of components that are even, like here. I see that the line splits in another number of components that are not explained by the calculation I did before. And so that was a great puzzle at the beginning of the quantum mechanics, as you know. And for instance, there is this famous quotation of Pauli, who tells that a colleague who met me strolling rather aimlessly in the beautiful street of Copenhagen when he was staying with Niels Bohr, said to me in a friendly manner, "Pauli, you look very unhappy," whereupon I answered fiercely, "How can one look happy when he is thinking about the anomalous Zeeman effect?" And the first explanation was given by the physicist Alfred Landé in 1924, very beginning of the quantum mechanics, where he said that somehow he constructed a model of the atom using, you know, the Sommerfeld, Bohr-Sommerfeld atom of model of the atoms, that somehow could explain that mj. So we could write that as mj times j as a function of this parameter times the Bohr magnetons times the magnetic field. But this now has to be a half integer. And this, you need that somehow to explain the even number of components that are in the experiment. So we see now that there is half integer values that are possible somehow for the angular momentum. that you need somehow to inject in the theory to explain this anomalous Zeeman effect. And the comparison with the experimental data works remarkably well. So you have, that's also an amazing feature of quantum mechanics. It provides you with calculations that are not super complicated to do, and at the end, you can have a really crucial test with the experiment, and the comparison is always very good. So this was actually the signature of the spin of the electron. Somehow you need to add something more. And Pauli said then to describe this anomalous effect, then instead of having 3 quantum number, I will add a fourth quantum number. But that fourth quantum number, on which he was able then, using the Pauli exclusion principle, to construct the atomic table of elements somehow and explain the structure of the element, no one really knew what it was. And the first we introduced somehow what it was these 2 young persons, George Uhlenbeck and Samuel Goudsmit. They were graduate students of Paul Ehrenfest in Leiden. So you have this beautiful connection between here the work done by Pauli and the work done by these two young physicists. And basically, we have just to come back to another property, and this is very important for the following of the lectures. An angular momentum creates a magnetic dipole. There is a link between the angular momentum and the magnetic dipole. And this can be explained very simply using the classical model of an atom, which leads to the relationship connecting the magnetic dipole to the orbital angular momentum as mu vector is equal to gamma. Gamma classical is a gyromagnetic ratio times L. Okay, and if we now just do a very simple calculation, we consider that the electron orbiting around the proton, for instance, is equivalent to a current, okay? And we can use this to now reproduce the current times the surface of the coil. Here it's like a little coil inside the atom, and we define the magnetic dipole by simply the product of the current intensity times the surface of the coil times the direction, the unit vector perpendicular to the surface of the coil. And we have here the magnetic dipole definition, and that can be linked to the angular momentum associated to the circular motion, and we have simply this ratio where it is minus the charge of the electron divided by 2m, and this will define the geomagnetic factor. Okay, now using rotation invariance of the theory, we can actually show that a similar relationship also holds in quantum mechanics. And in any, if you start from J, the operator J, and an angular momentum, in a proper surface of eigenstates of J, we have this ratio. It's the application of the Wigner theorem, which are associated to vector operators. We don't need to go into those details. Now, once I have this dipole and I submit it to, for instance, a magnetic field, then there will be some forces acting on that. And basically, using a very simple model of the sphere, which is, for instance, rectangular, I can show that there is a torque applying on the field. This is just the demonstration of the formula that gives the torque. The torque gamma vector is equal to the product of the magnetic dipole times cross the magnetic field B, okay? And this has the effect to align mu of this torque wants to align mu with B. So somehow it's something you know. If I take a compass, the compass will take the direction of the magnetic field. And this is just the influence of this torque. Now I can show easily that the torque here derives somehow from a potential energy. So if I need to change the angle of the plane of the coil, I need some work to do that. And this work I have to do, for instance, if I go from a direction where the coil is in the plane of the plane of the coil is the magnetic field is in the plane of the coil, and I want to turn the coil by an angle alpha, then I need this work, minus mu magnetic dipoles times B cos alpha, and that tells you that you have a potential energy which is minus mu times P cross B. Okay? And so I can come back now to the potential, the interaction, as I show you, is V that previously, that I derived from the general expression of the Hamiltonian, is simply now, can be written in this way. I can identify here the magnetic dipole induced by the B field, okay? And what I see, it's exactly the same formula. So I have somehow two ways to understand my interaction of the magnetic dipole with the magnetic field. I can come back, I can use the first principles using the Hamiltonian and do lengthy calculation that will bring me somehow to this potential, okay? That's what I derived. But I can also have a more physical picture, which is simply the energy of the classical dipole inside the magnetic field. Okay? But the rigorous way is to start from, of course, a general Hamiltonian that I wrote previously. Okay, so now I can use that. And I can also do something different. I can now try to understand how this atomic magnetic dipole will behave in the magnetic field. And for that, I know that there is this link between the angular momentum and the magnetic dipole, okay? There's this proportionality, and I know how the magnetic field acts on the magnetic dipole. It's a torque. So now, if I apply the theorem of angular momentum, then I can easily show that somehow the magnetic dipole, if it has an angle with the magnetic field, the torque will be like that, and will turn the magnetic dipole along, it will wobbles around the B-axis, and this is a precession motion, okay? And we will call that the Larmor precession of the magnetic dipole along the B-axis of the magnetic field I apply. And this, the frequency of this motion is simply, again, the geomagnetic factor times the magnetic field. And this is important to remind, because we will come back to that many times in all our calculation of magnetic resonance. Okay, and the hypothesis of Uhlenbeck and Goudsmit was the following. I take an electron of mass m with this electric charge of minus e, and I say that it rotates along its axis as an electron spin, okay? And what they say, this electron spin, which is somehow an internal, we see like the electron as a ball and with this electric charge spinning on itself, will have an angular momentum, h bar over 2, and you have to put that somehow to explain the experiment, the anomalous Zeeman effect. Okay? So, what was the problem with that? We are still earlier than quantum mechanics, and somehow if we take this electron rotating on itself, and I compute now, and I say I take a classical model of the electron that tells me that the mass energy mc square, where c is the speed of light, is the electrostatic energy of a ball with a radius rc, and embedding the charge E of the electron. Then using this formula, I can compute the classical radius of the electron, which is of the order of 3 × 10⁻15 meter. Okay. Now I know the angular momentum, depending, of course, on how of the speed of rotation of this spinning ball. Okay, and this has to be equal to h bar over 2, taking into account what I said previously. So the speed of the equator, if I do this simple calculation, is c, the speed of light, divided by alpha. Well, alpha is the fine structure constant, which is equal to 1 over 137. So what I see is that the speed at the surface of the ball representing somehow the electron is much, much higher than the speed of light, which is, of course, impossible. And somehow we do not, this explanation by Uhlenbeck and Goodsmith has to face that issue. It's not consistent with this. And of course, somehow it was a kind of trick that they proposed to have that, and they were able also to go into fine computational details about the Zeeman effect and explain the value of J equal 2 of the dependence. But nevertheless, we have that problem. So you forget that. You say, OK, I don't mind that. This internal degree of freedom of the electron cannot be represented by this electric charge turning on itself. It's not possible. So somehow I integrate that in the theory. And it is actually Dirac that will provide the explanation where, using Dirac equation, where does it come from. And somehow it's deeply rooted in relativity. There are other ways also to explain the spin, but we forget that. OK, so now, once I have that, I had this extra degree of freedom, and I consider it, this internal degree of freedom of the electron, and I consider it as now I have to construct the Hilbert space in which that will describe this degree of freedom. OK? All that is a reminder, I guess, for many of you. But somehow it's a way to start. So I can now use all what I know from my general theory of angular momentum and apply it to this very specific, very simple case of an angular momentum value equal to 1/2. And this I will not call J, but S. OK? So I change a little bit my notation. I have eigenstate of S square and Sz, which are defined by S equal 1/2 and M equal minus plus 1 or minus 1/2 or plus 1/2. And then I will call that the first state will be called plus along Z, which tells me that I have set a quantization axis in the Z direction, which is physically associated in that case to like here, to the direction of the B field. And the other state will be called minus, OK, minus Z. OK, and for that, I can compute now, use all the things I learned. So Sz in this basis is, of course, diagonal. And Sz is simply h bar over 2 sigma Z. And sigma Z is a simple 2x2 matrix, 1, 0, 0, minus 1. I can also construct the operator Sx and Sy. So for that, I use the ladder operator S plus and S minus. From this state, now I can compute S plus, S minus. There is a mistake here. I will correct it. Sorry. OK. OK, I have S plus and S minus. And from that, I can compute Sx, the projection of the angular momentum vector S on the x-axis perpendicular to Z. And this is h bar over 2, again a 2x2 matrix, 0, 1, 1, 0. And this I will call sigma x. Same for the y direction. I have this formula, and now it's simply this new matrix, sigma y. And what I have here, it's the 3 components of Pauli matrices. Okay, so the spin 1/2 is associated to these 3 Pauli matrix. And the operator, Sx, Sy, and Ez are given by the Pauli matrix times h bar over 2. Okay? Now, what I can do is again use basic quantum mechanics to describe the behavior of a spin 1/2 in a static magnetic field. So for that, what I need to compute is the average value of mu, okay, as a function on a given wave function, given state psi over t. And psi over t will be described by the Schrödinger equation as I show here. This is the Schrödinger equation here, okay? So if I now use the Hilbert space that is done by combining the external degree of freedom of the atom, product the internal degree associated to the spin, I take, so now the Hamiltonian has two parts. One will describe the external degrees of motion. For instance, it can be associated to the Coulomb potential that bounds the electron to the nuclei, to the nucleus of the atom. And then I have these couple terms, the spin component, which is simply the term here, the magnetic dipole operator. I put a hat for each operator, as you have seen, times scalar product, the magnetic field. Okay? And this is simply mu z times B0. And I have now B is equal to B times mu z along the z direction, which z will be then the quantization axis. Okay, I suppose that initially the the state of the atom of the system has no correlation between the spin and the external degrees of freedom. And then as I have no coupling in this Hamiltonian between the two degrees of freedom, external and associated to the spin, we will remain in a product state. So we will have an evolution that this will go to this under the influence of this part of the Hamiltonian, and this will go to this under the influence of the Hamiltonian. As you may know, what I neglected at that stage, and that will be again important to remind when we will describe other defects in diamond, is, for instance, I forgot in this description, I do not take into account, for instance, the spin-orbit coupling. And the spin-orbit coupling, it's something that will couple now these different degrees of freedom, as we will see later on. Okay? So I do not take that into account. So with a very simple description, I have now just a separate evolution of the part of the wave function associated to the spin. And this is simply a component that will depend, that will be represented by a vector of dimension 2, which will be the projection of this part of the component onto the state psi plus and minus, describing the spin 1/2. Okay? And when I've done that, then I can now use again my equation, take into account the spin interaction with the magnetic field, which I can rewrite as a function of the Larmor frequency minus gamma B0. I remind you, the Larmor frequency, the classical image, is a frequency associated to the precession of the magnetic dipole in the system. And H will be proportional to H bar omega 0 divided by 2, the Pauli matrix sigma z. Okay? Now what I see is that the state plus and minus that describe the spin 1/2 with the z direction will remain eigenstate of this Hamiltonian, describing the coupling of the spin 1/2 with the magnetic field, but now with different energies. Initially, those two states are degenerate, and when I apply the magnetic field, now those two states have energy plus minus h bar omega 0 divided by 2. If I come back to Landé rules state me that if I take any systems, like for instance an electron, then the energy will be ms Js mu b times b, mu b being the Bohr magneton. Ms is plus minus 1/2, and mu b is equal to mu e h bar over 2m. This means that somehow, if I use the spin 1/2, there is a subtlety. I need to change the value of this Landé factor. Now it has to become 2. Before, when I was only considering, for instance, an orbital angular momentum L equal 1, I had exactly this. I could describe the 3 components, the 3 energies of the system by the same formula, but in that case, J for L equal 1 was equal to 1. So I have a subtlety. I have a difference of the J value, which is 2, if I want it to be in agreement with my observation and all the calculation I have done. So this is quite bizarre. So somehow at the end you say, okay, why do I need to do that? Because somehow I have 2 here and 2 here. I can simplify and simply take into account the formula, remind the formula, which tells me that mu, the magnetic dipole associated to the spin, 1/2 is equal to minus the charge of the electron. This is simply by I have a negative charge, the E charge here, divided by the mass times S, the value of the angular momentum, h bar over 2 in on projection of a given axis. But I want to keep that. And I will try to explain what is the physics behind that to remind you a little bit. So again, the Larmor precessions tells me that. It's given as, this is the frequency difference. Okay, I've rearranged it using this geomagnetic factor of 2. At the same time, I can look to another influence of the magnetic field. We have an electric charge. So the electric charge as, the magnetic field impacts the spin of the electrons through this precession motion, or in quantum mechanics with its different eigenstates. But it can also influence the motion of the electron in the magnetic field. Okay? There is a Lorentz force acting on the electron, and for that, we have a uniform circular motion in the plane xy at a given frequency, which is a cyclotron frequency. And you see that the cyclotron frequency, which is just the classical motion of the electron in the field, is exactly the one I have from the Larmor precession. So the 2 are in agreement. That's what my calculation said. If the gyromagnetic factor associated to the spin of the electron would be 1, like in the case of angular momentum L equal 1, that means that I would have a factor of 2 of difference between those 2 frequencies. Okay? So both motions are synchronized and occur at the same frequency. And remarkably, this has been checked in experiments, in measurements, realized on a single trapped electron by Hans Demmelt, who got the Nobel Prize for all this beautiful work, and Gerald Gabrielse. And they could trap, for instance, a single electron for a year and in this penning trap. And then they had the motion of the electron that could be measured by detecting somehow the influence of the charge on the different elements of the quadrupole that was used to trap the electron. And at the same time, they could measure the frequency difference with a great accuracy associated to the Zeeman effect occurring on the spin 1/2. That was spectroscopy experiment, as I will show later. So they could do the same kind of thing. They could measure independently, very accurately, the cyclotron motion, and at the same time, measure how the magnetic field applied on the electron modify the system. And for that, they could determine that indeed the 2 motions, precession and cyclotron motion, occurred at the same frequency omega 0 and omega c. But they could also, but it was not exactly, but they could also determine the value of J. If I take into account here I should put the value of J, whereas here I do not have the value of J. Okay? And by measuring with remarkable accuracy these two frequencies, they could really determine that J over 2 was not equal, was not 1, but 1 plus something. And plus something, now it can be measured with an accuracy of 10 minus 13. This is the highest accuracy that one can obtain in physics, in the measurement of a physical constant now. There are clocks, optical clocks now that have been developed, which has an accuracy at 10 minus 15, which are a little bit higher, and that can be somehow now used somehow to determine this parameter, because of course, to measure the frequency, somehow you need to synchronize your synthesizer, for instance, to a to a very accurate optical clock, because otherwise you don't know how to do it. And this is done now. This can be certainly done using these optical clock developments to even, in the future, to even higher accuracies. And to understand the difference here, you see that the difference is 1.00112, something like that, 1 or 16. This was actually done just after the Second World War by quantum electrodynamics calculation using by 3 people, Schwinger, Tomonaga, and Feynman. The first who did the calculation somehow was Schwinger, and using some very sophisticated calculation, he could explain that somehow the difference of the J value, the fact that J over 2 is not exactly 1 for the electron, has to take into account the influence of the electron with the quantized electromagnetic field that in which around him, and this is vacuum, but vacuum, as you know, in quantum mechanics, has fluctuations. And it is the interaction of the electron with this vacuum fluctuations of with the quantum fluctuations of the electromagnetic vacuum that gives this value of J a little bit different than 2. Okay? And he could measure that the difference was somehow the fine constant structure divided by 2 pi plus another term as alpha square, etc., etc. So he could obtain like that a perturbative measurement. The idea was before, but somehow what was very strange at the beginning was that these perturbation theory, if you apply it for many, many terms, do not converge. It goes to infinity. And of course, that would lead to, that's not possible, physically possible. And it's Schwinger and Tomonaga and Feynman who found tricks to understand why this is not going to infinity. And Feynman did somehow introduce what are now known as the Feynman diagrams to get pictures of how to do this development on here, and and today this is a way somehow to measure the fine constant structure, and the fine constant structure using these developments can be determined using this calculation with this value. And what is remarkable is that the computation has an uncertainty which is larger than the one you can measure. So somehow you have an experiment that has an accuracy which is much higher than the one of what you can do even with very, very sophisticated calculation. Okay, and for instance, this value was obtained by taking account almost 1,000 Feynman diagrams into all that, and you can imagine how difficult such calculations are to describe the coupling with the quantized electromagnetic vacuum of the electron. Okay. I think we can make a quick break here for 5 minutes, and then we go to, now I know I reminded you a little bit what is the spin of an electron. Now, since we know also that the proton is a spin 1/2, what can we say about the magnetic dipole associated to the spin 1/2 of the proton? Okay, we make 5 minutes break, 5-10 minutes, and then we continue. So I know that certainly you have seen all that, but it was a way to to settle the notation and remind you a few things that we might need in the following of the course. Okay, we take 5 minutes.